Alright, CNT140, we're continuing on with Chapter 7 here on our connectors. We just got done with the epoxy polish. So the next style is your hot melt adhesive. The process is going to be almost identical. It's just instead of using epoxy in there, we're using basically hot melt glue, hot glue if you will, if you want to think of it that way. So this is the style right here, and this is the part in here that gets heated, that you fit the fiber through out the end, let it cool, and then scribe and polish off. So strip off the buffer, heat it up, fit your fiber through. Once it cools, scribe the end, cleave off the fiber, and then polish it back just like you did on the epoxy polish style. Next style is basically, you could think of it as like, your crazy glue, your fast setting, your quick setting adhesive. Again, the process is pretty much the same. Here's your fast glue fiber connector. Strip the buffer, fish your adhesive. There's showing you basically, you think of it as like super glue if you will, crazy glue. Okay, fit the fiber through the connector. Once it cures, scribe, cleave off the fiber, and polish it back flush with the end of the ceramic ferrule. There was a style used for a while, crimp and polish. And actually, this was a style we used in the lab room for a while. And I would agree with the iffy performance. Our success rate was not very high on these in the lab room. So here, it was meant to be a style of kind of like faster termination without all the epoxy and glue. So what happened here was the connector body. This was a factory terminated fiber here that was factory polished, and this fiber was basically sitting here. This piece here was factory installed and polished, and this was sitting here. You would prepare your fiber, slide it in here till they touched, and then you would crimp your fiber in place. So this is kind of flipping it around. Here's the ceramic ferrule, and this is the pre-polished fiber stub that the factory put in. You would prepare your fiber, slide it in till it just touched, and then you would crimp the fiber in place to hold it. That was the process that was done. And you would use these type of fixtures. Here's a Corning fixture. This is the kind we had. That once you fit the fiber in place, you crimped a little sleeve back here to kind of hold the buffer in place, hold the fiber buffer in place. So the process now would go, you strip the buffer off, clean it, cleave it, carefully slide it into it just touched. You couldn't jam it in, you couldn't turn it around, just so it just touched, and then you would crimp that little sleeve on the back to hold it in place. And again, our success rate was not very high on ours. Kind of the more modern style that's used is the splice-on connector. Splice-on connector. This is the style we're going to use in the lab room. Here, it's kind of similar to the crimp. You have a connector that here's the ceramic ferrule. The factory installs the stub here for you. And what you do is you prepare your fiber and then you fusion splice their factory stub onto your stub that you prepare. So using a fusion splicer here. This fusion splicer here, here is the connector that is pre-terminated by the manufacturer at the factory. Here's the fiber that you prepare, and your stub comes in here. Their factory stub comes in here. These two electrodes, the little silver points, look like little pencil points. Those are the electrodes that strike an arc across, almost like you're arc welding. They heat up the end of those two fibers, and then the machine itself gently slides those two fibers together till they touch. The arc stops, and it just kind of sits there and holds them in place till the glass cools, and those two fibers then are fused together. And then all you have to do is put the connector body and everything back over it for protection. And this is what basically you get from the manufacturer. This right here is the ceramic ferrule. This is the end of the connector you would actually plug into a port. This is the connector body, if you will. Here's the fiber stub that you're going to fuse onto. So what you do, strip your buffer again, clean it, cleave it, load it into the fusion splicer. Here's the fiber that you're preparing, load it in. This side has on the this part here that you get from the manufacturer, the prepared part, if you will. You then basically hit the run on the fusion splicer, this guy right here. These two little windshields close over top. And then, like I said, an arc gets struck across here to heat up both fiber stubs. And then the machine takes those two little stubs and slowly kind of wheels them towards each other till they touch and then lets it cool. Up here as well. When it's done, you do need to put a splice sleeve over to protect that termination where those two stubs meet. And we'll show you that in the lab room. We'll show that splice sleeve going over top to protect. So some hints they have for field terminations, follow the directions carefully, choose the right connector, know how to use it. You're not going to learn out in the field, learn in a lab environment, if you will. Have the right tools, clean everything, keep everything prepared. Dust and dirt of the enemy. Do not over polish if you're actually going to do the epoxy polish. Regularly change the polishing film again if you're polishing. Cover connectors and patch panels will not use dust caps and so forth. And then inspect and test. Inspect and test that. Do you have to terminate in the field? Not necessarily. Remember we said before, you can order cables to length. You do need to do some work to get the right length. They'll put the ends on for you. When you get the cable, you can pull it through your inner duct and install, if you will. So you can actually get fiber like so. If I am terminating or pulling fiber and terminating, I might need some protection, whether it be patch panels or breakout boxes or whatever. I might need protection for those, so I might need to plan for that in my equipment racks. And that's what they say about your multi-fiber push-on connectors and so forth. They have lower loss. Factory assembled is lower loss. They're not they're not low loss, but a little bit of loss. It can be a trade-off because of the high fiber count and less install time. When we talk protection, any of our terminations, we're either using some sort of patch panel with support and support tray or something like that to protect our connections, or as I'm doing an outlet box, I would have an outlet box that actually is going to protect the fiber and do the connection in that for protection, protecting those connection points. On to splicing. A splicing is create a permanent joint between two fibers, and again, we can either do a fusion or mechanical. Most common application when you're joining cables in long outside runs. I have one run that's 1 kilometer long. I have another one's 1 kilometer long. I join those two together. So that is on your single mode mostly. Not a whole lot on multi-mode. A lot of time multi-mode you end up using a mechanical splice. Here is an actual fusion splice, and these are all kinds of different mechanical splices that can get used. The fusion splice is going to use that fusion splicer we just showed you, create an electric arc, touch the two fibers together, and basically make it look like one actual original piece of glass. The mechanical splice is going to be a fixture to hold it in place, and then there's a little bit of index matching gel between the two to help with the loss. Fusion splicing is most widely used, especially for single mode. Mechanical splicing tends to get used for multi-mode and for temporary restoration, repairs, if you will, quick repairs. Fusion splices, again, they're welded together using that fusion splicer, but they're typically done in a kind of a clean environment, a truck like so that I would actually bring the fibers into and splice and then install them in, using a table with all your tools and everything on to keep the dust at bay. Your fusion splices are automated. You can actually put some settings in for the different types of fibers, and then after you load the fibers in, you can basically hit a run button, and it does the whole close the windshield, strike the arc, roll the two fibers together, let them touch. Arc goes away, lets them cool, and then pop the windshields open, and then you can move the fiber over and put the splice sleeve on for protection. You can do one at a time, but there are machines that'll do 12 at a time. Here's a single fiber fusion splicer. This looks very similar to the one we have in our lab room that we'll be using, and they do make a ribbon cable splicer. This would do 12 fibers at one time. Okay. This actually is a 1 fiber, but it's showing you kind of a top view and a side view. That's what you're seeing there. Here's 12 fibers being terminated to 12 fibers. The fusion splice, yes, I'm going to strike an arc. I have the 2 fibers coming together, the electrodes strike an arc, and then the machine itself gently wheels those 2 together till they touch and lets it cool off. And then you have basically a single fiber there. The process, strip the buffer, clean it, cleave it, put it in the fusion splicer, and I would repeat the same process on the other fiber over here. The machine itself, there's the 2 fibers laying in those channels. There's the arcs, or the 2 electrodes. The arc strikes across there to heat these up, and then each fiber side slowly wheels towards each other till they make contact. And this is showing you the fusion splicer up on the storage box, but 1 fiber coming in this side, 1 fiber coming in that side. When you're done splicing, you slide a splice sleeve over top. In this right here, there's a metal spline in there to give rigidity to that fiber, the fiber connection. And then this right here is a heat shrink tube that basically you heat it up and it shrinks around the fiber and gives you a strong protection against strong protection around that fusion splice. They do make mechanical splices. And it's basically a fixture to hold the 2 fibers in place, and then there's usually a little index matching gel between the 2 to reduce the amount of loss. Here's kind of a close-up of one, showing you fiber, and then this mechanical contraption clips around it, and you screw it tight to hold it in place. And then here's a different style of mechanical splice, kind of a round tube style. And the process, again, is very similar. Strip off the buffer, clean the fiber, cleave it, slide it in, do the same thing on the other side. Making good splices, cleanliness is a big issue. The cleavers are super important for getting good, clean ends of the fiber to splice together. As we use our cleaver in the lab room, we'll show you, it almost looks like a pizza wheel that you're cutting pizza with, and it nicks the fiber and cleanly breaks off the end of the fiber. And when I have 2 clean breaks, I can fuse those together. Fusion splicers need to be properly maintained and cleaned. Before we use ours in the lab, I usually spend some time servicing it and cleaning it so it's ready to go. Mechanical splices needs to be light pressure on those 2 fibers touching together. And in some cases, you can actually do terminations with the visual fault locator, and that'll help you make sure you have a good termination. Splices require protection. Here shows you an example of like premise cabling. You actually have a splice tray here. There's actually little grooves in there that the splices lay into, and then out 2 connection points. So you might need some sort of tray to protect them. Outside plant, you have the same thing, but you also need some sort of protection over top for, maybe it's going in under dirt or underground, so I need protection that way, but I also need moisture protection too. We don't want any water getting in there and degrading the fiber before the cable, degrading the fiber cable too early. I'll get it yet. Splices require placement of protective cases. Cables with metallic shielding will need to be properly bonded and grounded. And then outside plant enclosures should be sealed to prevent moisture, and that's why I showed you that example. Choosing a splice, performance should be a kind of a consideration. Fusion splice gives low loss, low reflectance, preferred. Fusion splice may not work on some monomo fibers, so mechanical might be chosen. So there might be a choice for you. Reliability, fusion splice is your best choice. Properly made, it should last as long as the cable. Cost, well, fusion splicing equipment, as we're going to see, is pricey, and all the tools required is pricey too. So the splices can be cheap per slice once you have all of that equipment. But if you don't have all that equipment, mechanical splice might be the cheaper way to go, but mechanical splices overall are more expensive than a fusion splice. So it is kind of a trade-off on cost, depending on kind of how many and when you need it. So there is all the topics in 7.